In this video, we're going to take a quick look at trigonometric functions. We'll start by looking at sine and cosine. We define the sine and cosine functions using what we call the unit circle. The unit circle is the circle having equation x squared plus y squared equals 1. That is, it's the circle centered at the origin, 0, 0, having radius 1. So the radius of this circle is 1. The next step is to draw what we call a central angle. A central angle is one that has the vertex at the center of the circle. So one side of the angle is the positive x-axis, and the other side of the angle is what we call the terminal side. We want this angle to have radian measure theta. The terminal side of this angle will at some point intersect the circle, and where it intersects the circle, we have a point with an x-coordinate that we call cosine of theta and a y-coordinate that we call sine of theta. And this is how we define the cosine and sine functions. Because of this definition, they're often called the circle functions or the circular functions. Sine and cosine have a strong relationship to right triangles, and we can see that exhibited in the definition. The point with coordinates cosine theta, sine theta is marked here on this circle. If we draw a radius going from the origin to this point, which again is the terminal side of the angle, and then if we drop a line perpendicular to the positive x-axis in this picture, we can see that we create a right triangle. The sides of this right triangle have hypotenuse 1, and the two legs are cosine theta and sine theta, because the x-coordinate tells us how far out along the x-axis we've gone, and the y-coordinate tells us how high up above the x-axis we've gone. This picture works out very nicely because we're in the first quadrant. If we were in a different quadrant, one or more of these coordinates would be negative. We could still get the same picture, but we just have to reinterpret these values in order to get a geometrically significant object. For example, if we were in the second quadrant, we might have something like this picture. And now the angle theta would go all the way around here. So now theta is greater than 90 degrees. So in this case, the point would still have coordinates cosine theta and sine theta. But now cosine of theta is negative. So instead of viewing this length as cosine of theta, it's now the absolute value of cosine of theta. That will give us the length. Sine of theta is still positive, so that still gives us the height, sine of theta. At any rate, we can see that there is a relationship between cosine of theta and sine of theta on the circle that also appears in terms of these right triangles. Both of these triangles are right triangles. And we can exploit this relationship to compute certain values of cosine theta and sine of theta. Our first example is theta equals pi over 4, or 45 degrees. If that's the case, if you have a 45-degree angle, then this is a 45-degree right triangle, so it's an isosceles right triangle. This angle here, of course, is necessarily 90 degrees, or pi over 2. It's a right angle. So that means that if this angle is pi over 4, then this angle must be pi over 4 as well. So if you have the base angles equal, that means the corresponding sides are equal. So this is an isosceles right triangle. So in particular, if you know that the hypotenuse is length 1, that necessarily means, because of the Pythagorean theorem, that each side is the square root of 2 over 2. Consequently, since this angle that we were calling theta is pi over 4, we can conclude that cosine of pi over 4 is the x-coordinate, square root of 2 over 2, and sine of pi over 4 is the y-coordinate, which is also square root of 2 over 2 in this example. Another important example is pi over 6, which is 30 degrees. In this case, we have a 30-degree, 60-degree right triangle. If this angle is pi over 6, that means that the other angle is pi over 3, or 60 degrees. Once again, we have a right angle. So what do we know about a 30, 60-degree right triangle? Well, we know that the shorter side is half the hypotenuse. So that tells us that this side length is 1/2. That gives us the y-coordinate, so the y-coordinate is 1/2. Furthermore, the length of the longer side, or the longer leg, I should say, is square root of 3 over 2. Consequently, the x-coordinate is square root of 3 over 2, so that's the value of cosine at pi over 6. The y-coordinate is 1/2, so sine of pi over 6 is 1/2. And that's what you get if theta is equal to pi over 6. Another important angle is pi over 3, which is 60 degrees. Well, in this case, you still have a 30, 60-degree right triangle. It's just that now the shorter leg is along the x-axis. So the shorter leg has length 1/2, and the longer leg has length square root of 3 over 2. So that tells us what the x and y coordinates are. So the x-coordinate is 1/2, and the y-coordinate is square root of 3 over 2. The x-coordinate is cosine of pi over 3, so cosine of pi over 3 is 1/2, and sine of pi over 3 is the y-coordinate, which is square root of 3 over 2. So just using the geometry of the unit circle, we can determine the values of sine of theta and cosine of theta for many significant values of theta. So for example, we've already found the values of sine and cosine of pi over 6, pi over 4, and pi over 3. Another important value is when theta is equal to 0. In that case, we're at the point, well, when theta is equal to 0, we're actually along the positive x-axis at the point 1, 0. So that tells us that cosine of 0 is 1 and sine of 0 is 0. Another important theta value is pi over 2, which is 90 degrees. In this case, we're now on the positive y-axis at the point 0, 1. So that tells us that cosine of pi over 2 is 0 and sine of pi over 2 is 1. Similarly, we can find the other two intersection points where we're intersecting with the x-axis or the y-axis. Notice that there are some other values on this image. We could similarly use right triangles to determine the values for, say, theta equals 2 pi over 3 or 7 pi over 6. But we don't need to do that. We just need to use the fact that the unit circle is symmetric about the x-axis and the y-axis. So we can make use of what they call the reference angle. For example, let's look at 5 pi over 6, this one right here. 5 pi over 6 has a reference angle that is 1 pi over 6. The reference angle is the smallest angle that's made with the x-axis. So that's this angle here, which is pi over 6. I know that it's pi over 6 because I know that 180 degrees is pi. So the angular distance between 5 pi over 6 and pi is 1 pi over 6. That's my reference angle. Now how do I use the reference angle? Well, if I look at the angle pi over 6 in the first quadrant, I can see that this point 5 pi over 6 is the reflection of pi over 6 through the y-axis. So what does that mean? That means that the height is the same, 1/2. the distance away from the y-axis is the same as well, just in a different direction. So instead of moving to the right by square root of 3 over 2, instead I'm moving to the left by square root of 3 over 2. Moving to the left means that I have a negative sign in front. But you can see the values are the same, it's just that one is positive and one is negative. Similarly, if I look at 7 pi over 6, this also has a reference angle, which is pi over 6. The reference angle is the smallest angle that's made with the x-axis. So again, it's pi over 6. And you can see that since I'm in the third quadrant, I've reflected the point at pi over 6 through the y-axis and then through the x-axis. So now I'm down here. That means I've gone to the same distance to the left as before. So the x value is the opposite of the square root of 3 over 2. I'm down here now. But since I'm reflecting through the x-axis, that means instead of going up by 1/2, I'm going down by 1/2. So that's why it's a negative 1/2 here. So we're just using the properties of the circle and the fact that it's symmetric about the x-axis and the y-axis. So in fact, if you find the reference angle, then the values for sine of theta and cosine theta are going to be the same as the values for sine and cosine of the original reference angle. But you just have to determine if it's a plus or a minus, and that's determined completely by which quadrant you're in. If you're in the first quadrant, they're both positive. So this is the first quadrant here. The second quadrant over here has x negative and y positive. The third quadrant is down here, and this one has both negative. Then over here in the fourth quadrant, we have positive x values and negative y values, and you can see that here. All of these x values are positive, but the y values are negative. And all of the values in the fourth quadrant are the reflection of the values in the first quadrant through the x-axis. So all of the y values stay the same. Square root of 3 over 2, square root of 3 over 2, square root of 2 over 2, square root of 2 over 2, 1/2, 1/2. The y values are the same as well, except they have a negative. So here we have a positive 1/2 goes to minus 1/2. Positive square root of 2 over 2 goes to negative square root of 2 over 2. And positive square root of 3 over 2 becomes negative square root of 3 over 2. That's actually true with pi over 2 and 3 pi over 2 as well. See, the y value for pi over 2 is 1. Then you reflect it through the x-axis to get theta equals 3 pi over 2. And now you can see that the x value is the same, 0, and the y value is now the opposite. We can use these values to help us look at the graph of sine and cosine. So let's start with the graph of sine. Now, here we have our unit circle, which is just x squared plus y squared equals 1. And sine is the y-coordinates. So we just want to look at the y-coordinates, the second coordinates, 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. Now on this graph down here, our x-axis is the horizontal axis and our y-axis is the vertical axis, where y is equal to sine of x. So we're actually thinking of x as being the angle here. So as we're moving along the x-axis, we think of the angle as increasing. It passes through pi over 6, then pi over 4, then pi over 3, then pi over 2, and so on. So as we're moving along this axis to the right, we imagine moving around the circle in a counterclockwise direction. So we start here, and then we move up. We pass first through the angle 0, then pi over 6, then pi over 4, then pi over 3, then pi over 2. So those are these values here. And you can see that we start at y is 0, then 1/2, square root of 2 over 2, square root of 3 over 2, and 1. And if we trace that out, that gives us this. Let me try that again. That gives us this. So we start at angle 0 and we get a 0. So that means we're here at the origin. And then we increase until we get to the angle pi over 2, which is right here. And then our y value is 1 right here. So it's 1. Now, we then start passing through the same numbers just in the reverse order. Square root of 3 over 2, square root of 2 over 2, 1 over 2, and then 0 over 2. So now we're just doing the same numbers in the reverse order, and so that's why you get this sort of symmetric picture like that. Once you get to an angle of pi, you're back at 0. And then you pass through the same numbers again, but now with negatives in front, so they're below the x-axis. So just like so. And then you pass through the same numbers again, but in the reverse order. And then you end up essentially back where you started, right here. So when your angle is 2 pi, that means you've gone all the way around the circle. So when your angle is 2 pi, that means you might have gone all the way around the circle, but you just ended up where you started. So you're back at 0, right here. We can do the same thing with cosine. So here's our graph of cosine. So we proceed in exactly the same way. As we're moving along the positive x-axis to the right, we're moving along the circle here in a counterclockwise direction. But now, instead of looking at the second coordinate, we're looking at the first coordinate. So we start at 1, and then the square root of 3 over 2, square root of 2 over 2, 1 over 2, and then 0. So we start at 1, and then we pass through our usual set of numbers until we get to 0. And then again, the same numbers, but now negative. Minus 1/2, minus square root of 2 over 2, minus square root of 3 over 2, minus 1. And as you can see, we're passing through those numbers, but now they're negative here until we get to negative 1. And then we start doing the same numbers in the reverse order, and we end up finally to 0, and then we keep going until we get back to where we started. Now, when I say back to where we started, that means we've gone around the circle one time, one complete revolution, and we're back to 1, which is right here. So this is the graph of cosine. You can determine some properties of sine and cosine based on the circle definition. So for example, we have a circle here which is the circle of radius 1. So that means its equation is x squared plus y squared equals 1. So just based on this equation and the properties of the circle that it describes, we can say certain things about sine and cosine. So for example, we can say that both sine and cosine have domain, the set of all real numbers. That's because we move in the positive direction going counterclockwise. And if you start at 0 and you go all the way around to 2 pi, you can just keep going. You can just keep going to 4 pi, 5 pi is here, 6 pi, 7 pi is here, 8 pi back where you started. So you can just keep going and going and going and get all of the positive numbers. You can get the negative numbers by just going in the reverse direction. So in terms of angles, when we have a negative angle, we think of that as moving in the opposite direction. So negative theta would then be moving in the clockwise direction. So if you're moving in the clockwise direction, that's a negative number. So in this way, you can have all of the positive numbers and negative numbers as members of your domain for sine and cosine. 0 is also in the domain because that's the starting point. So you can see that the domain is the set of all real numbers. What about the range? Well, the range is between -1 and 1 for both of them, because those are the extreme values for x and y. If you look at the x-axis, the x-intercepts are at 1 and -1. Same for the y-axis. The maximum y value is 1 and the minimum y value is -1. One of the other properties that you can observe is what we call periodicity, and we've already commented on this. Periodicity just means that it repeats, and both sine and cosine have period 2 pi, because we've observed that if you go around the circle, which is a revolution of 2 pi radians, then you end up back where you started. So then you just start over and do the same thing again. So every time you go around the circle 2 pi, which is one complete revolution, you just start over. You do that for both sine and cosine. So they both have period 2 pi. Another identity, or another property which is very important, is the Pythagorean identity. And that's for any theta, cosine of theta quantity squared plus sine of theta quantity squared is equal to 1. That just comes from this equation of the circle. We know that x squared plus y squared is equal to 1. That's the equation of the circle. And the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. So you just plug in x equals cosine of theta and y equals sine of theta, and what do you end up with? You end up with the Pythagorean identity. Let's just look at the sine graph for a moment. Let's look at some of the characteristics of the sine graph. Well, we've already commented on some of them. The sine function is periodic with period 2 pi, so every 2 pi it repeats. You can see one period here. There's another period over here, as you can see. It doesn't matter which direction you go in, it repeats. The domain is the set of all real numbers, as we mentioned, and the range is the set from -1 to 1, because you can achieve -1 and you can achieve +1, and those are the extremes. Notice that the sine function is also an odd function. That means it's symmetric about the origin. If I spin this around the origin 180 degrees, I end up with the same graph. The characteristics of the cosine graph are similar, and that's not a coincidence. The cosine function is also periodic with period 2 pi. Again, you can see one period here, but also in either direction you get the same repetition. The domain of the cosine is minus infinity to positive infinity. That is, it's the set of all real numbers. And again, the range of cosine is the set from -1 to 1, including the endpoints. The cosine function is an even function, which means it's symmetric about the y-axis. So if you reflect through the y-axis, you get the same thing. Now, I mentioned that it's not a coincidence that sine and cosine have a lot of similar properties. That's because cosine, the graph of cosine, is the same as the graph of sine, just shifted by pi over 2. Let's look at some of the identities for sine and cosine. Well, one we've already mentioned, the Pythagorean identity. Cosine of theta quantity squared plus sine of theta quantity squared is equal to 1. This is the identity that everybody should know. Here are some other identities that will be very useful whenever you're doing calculus. The double angle and half angle identities. So sine of 2 theta, for example, is 2 times sine theta times cosine theta, and cosine of 2 theta is cosine of theta squared minus sine of theta squared. And another way of writing it is 1 minus 2 times sine theta squared, or another way of writing it is 2 times cosine theta squared minus 1. We also have these identities here, which you can call the half-angle identities, or the reduction formulas. These are also known as reduction formulas. These are called reduction formulas because they reduce the degree. So we have sine theta quantity squared, but we get rid of the squared by rewriting it as 1 minus cosine of 2 theta divided by 2. Cosine of theta quantity squared is 1 plus cosine of 2 theta divided by 2. We go from a squared to something which is not squared. So that's why it's called a reduction formula. You can also think of it as a half or a double angle identity depending on your point of view, because this angle, theta, is half of this angle, or alternatively, this angle is double this angle. We also have the sum and difference formulas, and in fact, these double angle and half angle formulas really come from the sum and difference formulas. So for any angles alpha and beta, we have sine of alpha plus or minus beta is equal to sine of alpha times cosine of beta plus or minus sine of beta cosine of alpha. So if sine is alpha plus beta, then you choose the plus here. But if it's alpha minus beta, then you choose the minus here. So sine of alpha plus beta is sine of alpha cosine of beta plus sine of beta cosine alpha. And if it's a minus, you choose the minus. Now if you have cosine of alpha plus or minus beta, then the sign changes direction. So cosine of alpha plus beta is cosine of alpha times cosine of beta. Now it's minus. So if you start with a plus, you end up with a minus. Sine of beta, sine of alpha. And if you start with a minus, you end up with a plus. So for the sine formula, the sine preserves the sign, but cosine does not. I mentioned a moment ago that the double angle and half angle identities follow from the sum and difference formulas. So if you imagine, for example, in this first formula, the sum formula for sine, if you take alpha and beta both equal to theta, then here you have sine of 2 theta, which is this one. And so then you end up with sine of theta cosine of theta plus the same thing, sine of theta cosine of theta. So that's where this formula comes from. And if you do the same thing for cosine and do theta plus theta, so alpha and beta are both equal to theta, and take the plus one, then you'll have cosine of 2 theta, which is this one. And then you'll have cosine of theta times cosine of theta, which is cosine theta squared. You take the opposite sign, you started with a plus, so you have a minus sign, that's why there's a minus right here, and then you have sine of theta times sine of theta, which is sine of theta squared. Now if you use the Pythagorean identity on this identity, then you can reduce it to either 1 minus 2 sine of theta squared or 2 cosine theta squared minus 1. That's where these come from. And then if you solve for sine of theta squared or cosine of theta squared, then you end up with these two other formulas, these reduction formulas, just by solving for sine of theta squared or cosine of theta squared. So really, all you need to remember is the sum and difference formula, and if you remember those, then you could derive all of the others. Let's use our identities to solve some problems. For our first example, we're asked if sine of theta is 3 over 5, and theta is in the second quadrant, what is cosine of theta? So we can use the Pythagorean theorem for this. Before we start, let's try and figure out where we are geometrically. Well, it tells us that we're in the second quadrant, so that means if I draw my little unit circle, and just draw some axes here, we're in the second quadrant, so that means we're over here. In particular, what that means is that cosine is going to be negative and sine is positive. Well, we see that sine is positive, but what we need to keep in mind is that cosine is going to be negative. That's going to be important in a moment. So we're going to use the Pythagorean identity. Cosine of theta squared plus sine of theta squared is equal to 1. Now we know what sine of theta is. It's 3 over 5. So we have cosine theta squared plus 3/5 squared is equal to 1. So cosine of theta squared is equal to 9 over 25, or rather plus 9 over 25 is equal to 1. I was getting a little bit ahead of myself because the next thing we want to do is we want to just subtract 9 over 25 from both sides. And once you do that, you have cosine of theta quantity squared is equal to 1 minus 9 over 25, but that's 16 over 25. So cosine of theta is equal to plus or minus the square root of 16 over 25, which is plus or minus 4/5. And we need to determine if it's plus or minus, but we already know that. It's the minus one. So we want to select the minus one here. So it's minus 4/5. So that tells us that cosine of theta is equal to minus 4/5. And that's why we needed to know that it was in the second quadrant, because that's what told us if it was plus or minus. For our next example, we want to use an identity to find the exact value of sine of pi over 12. So there are a couple of different ways to do this. The way I like to do it is to use a sum or difference formula. Specifically, what I want to do is I want to rewrite pi over 12 as pi over 3 minus pi over 4. So you can check that this is in fact pi over 12 if you give them a common denominator. So this is 4 pi over 12 minus 3 pi over 12, which is in fact pi over 12. So these are actually the same thing. So what I want to use is I want to use the difference formula for sine. So sine of pi over 12 is sine of pi over 3 minus pi over 4. And so now we use the difference formula for sine. So it's sine of pi over 3 times cosine of pi over 4. And sine preserves the sign, so then it's minus. And now it's sine of, and you just swap the angles. So it's sine of pi over 4 times cosine of pi over 3. And now we just need to figure out what the values of these are, but we know sine and cosine for these values. The pi over 4 ones are particularly easy because those are the same. Those are square root of 2 over 2. Sine of pi over 4 is also square root of 2 over 2. What about pi over 3? Now, if you can't remember, you just draw a little circle and maybe draw in some axes here. And this is pi over 3, so that's this one, which is 60 degrees. So it's right there. So that's when the y one is bigger. So it's 1/2 square root of 3 over 2. So that tells us that cosine is 1/2, and sine of pi over 3 is square root of 3 over 2. So this is pi over 3. So that tells us that sine of pi over 12 is equal to the square root of 3 over 2 times the square root of 2 over 2, which is the square root of 6 over 4, minus the square root of 2 over 4. We can just write those as one term if we want, like so. And there's your answer. There are 4 other trigonometric functions, and they're all defined in terms of sine and cosine, or at least they can be defined in terms of sine and cosine. So we have tangent of theta is sine divided by cosine, secant of theta is 1 over cosine of theta, cosecant of theta is 1 over sine of theta, and cotangent of theta is cosine of theta divided by sine of theta. Let's look at their graphs. The tangent function is periodic, like sine and cosine, but the period is smaller. The tangent function is periodic with period pi. Why is that? That's because tangent is the ratio of sine to cosine. So when sine and cosine are both negative, you get the same values for tangent that you would when sine and cosine are both positive. So really we're just getting double the repetition because we can't see with tangent the difference between when sine and cosine are both positive and when sine and cosine are both negative. The tangent function is an odd function. This isn't really surprising because tangent is sine over cosine. Sine is odd and cosine is even. So if you have an odd function divided by an even function, you get another odd function. So that's why tangent is odd. And of course, being odd, that means it's symmetric about the origin. If I flip it around, if I rotate it around the origin, I get the same graph. And we can demonstrate that. If we just look at this little piece, for example, between minus pi over 2 and positive pi over 2, we can just rotate that and hopefully we'll see that we get the same thing. If we rotate it around the origin, there we go, we get the same curve. The domain of the tangent function is the set of all x's except the places where cosine of x is equal to 0. Now, cosine of x is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, all of the odd multiples of pi over 2, plus or minus, because you can have positive or negative x values. And you can see that in the graph Because every place where cosine is 0, every place where you're dividing by 0, you end up with a vertical asymptote. You end up with those vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, and also the negative versions, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and this continues out in both directions. Now, you can see in this graph there's a dashed curve. This is cosine of x, and every place that it crosses the x-axis, that's where cosine of x is 0. So cosine of x is 0 at pi over 2, 3 pi over 2, and 5 pi over 2, and so on. So every place where cosine of x crosses the x-axis, you get one of these vertical asymptotes. So you get a complete period for tangent occurring between vertical asymptotes. The range of the tangent function is the set of all real numbers. So even within just one of these little bands, say between minus pi over 2 and positive pi over 2, as x goes to negative pi over 2, your graph decreases towards negative infinity. That is to say, as you're moving to the left towards minus pi over 2, your function is decreasing without bound. On the other hand, if you're moving right towards pi over 2, then you're increasing without bound, so it's tending towards infinity. So that's why the range of the tangent function is the set of all real numbers. The secant function, so there's supposed to be a t there. The secant function, y equals secant of x. The secant function is 1 over cosine of x. Since cosine is periodic with period 2 pi, secant is as well. Secant is periodic with period 2 pi. The secant function is an even function. That's because cosine is an even function. And the graph of secant is symmetric about the y-axis because it's an even function. And you can see that here. If you reflect through the y-axis, if you reflect this curve, you get the same shape on both sides. Once again, we have a function that's defined in terms of cosine in the denominator. So the domain of secant is the same as the domain of tangent. That is, it's the set of all x values such that cosine of x is not equal to 0. So that's x such that x is not equal to plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. And in this graph, you can see once again we've got this dashed curve, which is y equals cosine of x. Every place where cosine of x is 0, the graph crosses the x-axis, and we have a vertical asymptote there. Now notice that in order to get a full period of secant, we need two of these bands. We have to include a vertical asymptote somewhere in the middle in order to get both pieces so that we get the full period of 2 pi. The range of the secant function is no longer the set of all real numbers. It's the set of real numbers from minus infinity to minus 1, including minus 1, and 1, including 1, up to infinity. So we include minus 1 and positive 1. We know that cosine is between minus 1 and 1. It's between minus 1 and 1. So if you look at 1 over that, you're going to get something which is bigger. You're going to invert it. So something that has size less than 1, so we're talking about a positive number that has size less than 1, if you look at 1 over that, it's going to have size bigger than 1. So here you have cosine, the size of it is between 0 and 1. So when you look at 1 over it, you end up with something which is bigger than 1. Now the exception to that is when it's actually equal to 1. 1 over 1 is 1. So any place that cosine is 1, secant will also be 1. So you have that at 0, you have that at 2 pi, you have that at minus 2 pi. And we can say the same sort of thing for negative values, negative outputs. Any place where cosine is negative, it's between 0 and negative 1. Again, the size of that is less than 1. So when you invert it, 1 over that, you get something that has a larger size. It just so happens that it's negative, so that's why it's extending downwards now. But again, the exception is when the output is actually minus 1. Now that happens at minus pi or positive pi or infinitely many other places. So any place where cosine is -1, secant will be -1 as well. The cosecant function is similar to the secant because instead of being 1 over cosine, it's 1 over sine. Sine is periodic with period 2 pi, so cosecant, being 1 over that, is also periodic with period 2 pi. And sine is an odd function, so cosecant, being 1 over an odd function, is also an odd function. So again, we see that we have symmetry about the origin. Now, if I was to draw in two of these pieces here like this, and we were to rotate these about the origin, we should get the same thing. There we go. So it's symmetric about the origin. It's an odd function. Now this graph looks very similar to secant, and again it is. It's just shifted over. And you can see that it comes in two pieces. We have vertical asymptotes every place that sine crosses the x-axis. So this dashed curve here is y equals sine of x, and it crosses the x-axis at 0, pi, 2 pi, every integer multiple of pi. And at every integer multiple of pi, you're dividing by 0, so you get a vertical asymptote. Similarly to secant, the range of cosecant is -infinity to -1, including -1, and 1 to infinity, again including 1. The domain of cosecant is the set of all x's such that sine of x is not equal to 0, so we're just ruling out all of the integer multiples of pi. We also have the cotangent function, which is 1 over tangent, and so you get all of the same kind of properties that you got with tangent. It's periodic with period pi, it's an odd function, and it's symmetric about the origin. The only difference is, since this is 1 over tangent, that's cosine over sine, now the domain is the set of all x's such that sine of x is not equal to 0. So once again, we're ruling out all of the integer multiples of pi. So that means we have vertical asymptotes at 0 and pi and 2 pi and minus pi and minus 2 pi and so on. So once again, the dashed curve here is y equals sine of x, and every place that it crosses the x-axis, that's where sine of x is equal to 0, and that gives us one of these vertical asymptotes. But once again, just like tangent, the range of cotangent is -infinity to infinity. Let's do another example. If sine of theta is equal to 3 over 5, and theta is in the second quadrant, then find the values of cosine of theta, tangent of theta, secant of theta, cosecant of theta, and cotangent of theta. Well, we're cheating a little bit because we already found cosine of theta a little bit earlier. So we're in the second quadrant, so we know that sine of theta is 3 over 5, but we've already found that cosine of theta is equal to the opposite of 4 over 5. So we found that earlier on some earlier slide using the Pythagorean identity. So now we can just find the other four functions. Once you have sine and cosine, then you can easily find the remaining functions just by rewriting them in terms of sine and cosine. So let's go ahead and do that. Tangent of theta is sine of theta divided by cosine of theta. So that's 3/5 divided by -4/5 is -3/4. Secant of theta is 1 over cosine of theta. So that means it's 1 over -4/5, which means it's -5/4. Cosecant of theta is 1 over sine of theta. So that's 1 over 3/5, which is 5/3. And finally, we have cotangent of theta is 1 over tangent, or cosine over sine, depending on how you like to look at it. Let's write it as 1 over tangent, and that's going to be 1 over negative 3/4, so that's negative 4/3. So just as a remark here, cotangent of theta is cosine of theta over sine of theta, but that's also the same thing as 1 over tangent of theta, like so. And that's our example. We have written down here the basic trigonometric identities. So we've already looked at the Pythagorean identity that you see here, cosine of theta squared plus sine of theta squared equals 1. You also have Pythagorean identities relating tangent to secant and cotangent to cosecant. These actually are derived just directly from the original one. So if you take the original identity and divide it by cosine theta squared, you end up with a 1 here. Sine theta divided by cosine theta is tangent theta, but you're dividing by cosine squared, so that's where that squared comes from. And then 1 divided by cosine theta squared is secant theta squared. Similarly, if you take the original identity and you divide by sine theta squared, then here you'll have a cosine theta squared over sine theta squared is cotangent of theta squared. Sine theta squared divided by itself is 1, and then 1 divided by sine theta squared is cosecant theta squared. So these two are achieved directly from the original, just dividing by cosine theta squared or sine of theta squared. So here we've just rewritten all of the even-odd identities, which we've seen already, and we're just really commenting here on the reciprocal identities and the quotient identities. All of these we've already talked about. Let's do another example. If tangent of theta is the square root of 3, and theta is between pi and 3 pi over 2, determine the values of cosine and sine. Well, this information on theta tells you which quadrant you're in. So let's just draw a little circle here, like that. Let's draw our x and y axes. So theta is between pi and 3 pi over 2. That means that it's in the third quadrant. So that means that we're over here between pi and 3 pi over 2. In particular, what that means is that they're both negative. Both sine and cosine are negative over there. So what we want to do is we want to figure out what tangent is. We want to write tangent as sine of theta over cosine of theta. Now, if that isn't obvious, then maybe if we just rewrite square root of 3 a little bit. So instead of writing it as square root of 3, we write it as square root of 3 over 2 divided by 1 over 2. Notice that we can do that because really we're just dividing the numerator and the denominator by 2. Square root of 3 is the same as the square root of 3 over 1. So we're just dividing the numerator and the denominator by 2. But we can get away with that because these are values of sine and cosine. So we're looking for a theta where sine of theta is the square root of 3 over 2, and cosine of theta is 1/2. Well, actually, remember that these have to be negative. So let's just put negatives in front of these. As long as we put a negative in front of both of them, it's fine, because this is the square root of 3 over 2 with a negative in front of it divided by 1/2 with a negative in front of it. So the negatives will cancel, and we'll end up with a positive number. Negative square root of 3 over 2 divided by negative 1/2. The negatives cancel, the 2's cancel, and you just end up with positive square root of 3. So we have that sine of theta is the opposite of square root of 3 over 2, and cosine of theta is the opposite of 1/2. So cosine is the x value, so it's minus 1/2, and then the y value is minus square root of 3 over 2. So we're at this point right here, negative 1/2, negative square root of 3 over 2. So we want to figure out what angle that is. And how do we figure that out? Well, really, we want to know our reference angle. So if I just keep going through here like that, to this point, this is 1/2 square root of 3 over 2. So this is pi over 3. And then over here, we have, this one's 2 pi over 3. And then pi is 3 pi over 3. So that means that this one right here is 4 pi over 3. Now if we wanted to keep going, this would be 5 pi over 3 over here. And then this one would be 6 pi over 3, which is 2 pi. So what we want is this one right here. So that tells us that theta is equal to 4 pi over 3. Now really all that we wanted to do was determine the values of cosine theta and sine of theta, and we've already done that. But even better than that, we even figured out what theta was.